Alright, what's up guys? In this video, I'm going to pick with some vector calculus and we're going to evaluate another surface integral here. Doesn't hurt to have multiple examples. This is actually example number 2 of the surface integral series where we are evaluating it using the definition of the surface integral. So this will be example number 2. And so let's continue to play around with it. So we got this surface integral y ds, where s is the surface, z is equal to x plus y squared, where x is between 0 and 1 and y is between 0 and 2. So we're just going to use the definition of the surface integral. Now you can evaluate surface integrals two ways. You can evaluate it using the definition, where you're given z is equal to some function g of x comma y. Or another way you can do it is by parameterization. Now that requires a little bit, that way of evaluating the surface integral requires far more work. Because there's a lot that kind of goes into doing it the other way. But I wouldn't consider it hard, but it is a little bit lengthier than just using your standard definition. So this is what I'm writing down here is the definition of our surface integral. If we're given some function z is equal to g of x, y, then this is how we evaluate it. And the formula is not hard to remember at all. I pretty much have it memorized. And yeah, it's not that bad. So just writing it down, it is quite long, but it's pretty straightforward. So this is the definition of the surface integral. Okay. Hopefully you guys can see. Hopefully the light isn't too bright. Hopefully. Okay. All right, so let's go ahead and go through and deal with it. So the first thing that we need to do is we need to specify what the ds part is. When you're looking at the surface integral here, again, the ds part is just the square root of the partial of g with respect to x squared plus the partial of g with respect to y squared plus 1, just your first order continuous partial derivatives. And that's what the ds is. So the function is given in terms of z is equal to g of x comma y. So we need to take the partial derivatives. In other words, g of x comma y is x plus y squared. Okay, let's take the partial derivatives and get that out of the way. So we need the partial of g with respect to x. So remember, when we're taking partial derivatives, we're treating the other variable as a constant. Okay, so in this case, we just get 1. And if we take the partial of g with respect to y, and it's pretty easy to see, we get 2y. Okay, so that gets that out of the way. Now I'm just going to set the surface integral up. We're going to simplify everything, but I do want to at least set it up. So let's just set it up. And when you set it up, this is what it should look like. So we got our double integral, and you can always tell the difference between a double integral and a surface integral by looking at the differentials. For the surface integral be ds, for the double integral be dA. And so what we do is we have our y, and then we got the square root of 1 squared plus 2y squared plus 1 dA. Now let's clean it up and take it from there. So remember, we're integrating this dy dx, so that means that the limits of integration corresponding to x need to be on the outside integral, and the limits with respect to y need to be on the ones that's on the inside when you're actually setting this up. Okay, so this is going to be y multiplied by the square root of, well, if we simplify this, we're going to get 2 plus 4y squared, and again, this is going to be dy dx. Now we just got a double integral. That's pretty much what we got here. So for the double integral, we're integrating with respect to y first from 0 to 2. So we can do a u substitution, and we know it's going to work because if we pick u to be what's on the inside of the square root, which is 2 plus 4y squared, although that's not the, technically that's not the derivative of what's out here, but if I take the derivative of this, I'll just get 8y, and that's going to cancel out a y basically. So the derivative, it doesn't have to be the exact derivative, but you just need to be able to cancel something out. So in this case, we'll pick u to be 2 plus 4y squared, and then that means that du will be 8y dy, and we'll end up with 1 over 8y du is equal to dy, and hopefully you see that the y goes. So it doesn't have to be the exact derivative. If it is, that's great, but it doesn't have to be. You just need to be able to cancel something out. Okay, well, so after we've done the simplification, remember 1 over 8 is a constant, can be brought out front. We'll need to change the limits of integration, so I'll leave the bounds blank right here, and then this will be the antiderivative of the square root of u du. Now let's just quickly change the limits, and make sure you're changing the limits. Anytime you're doing a u substitution for a definite integral, you gotta change the limits of integration, because the limits that you were given initially correspond to the variable y, and we're no longer working with y anymore. We're working with u now, so you need to have the limits for that. So what we do is we just stick in a 0 here, and if we stick that in, we'll get 2, and then we stick in a, what was the other limit? We stick in a 2, and don't forget that that's being squared, and in that case, that gives us 18. So now the new limits are from 2 to 18. So we got 1 over 18, that's just a constant. Remember, the antiderivative of the square root of u is 2 over 3 u raised to the 3 over 2. And now we need to evaluate that from 2 to 18. So the fundamental theorem of calculus says we plug in the 18 first, subtract what we get for that from what we get when we plug in 2. So sometimes, depending on the problem, well, to me, you should have a calculator anyway, just so that you can fine tune, make sure there is no arithmetic related mistakes, to have one near you. So make sure you have one, that way you can check your answers. In this particular scenario, I'm going to do just that. So I'm going to deal with the 18 raised to the 3 over 2. Again, most of this stuff can be plugged in a calculator. Okay, so 18 raised to the 3 over 2, I can just write that as 3 cubed multiplied by 2 times the square root of 2. Now we can end up canceling out one of these 3's. That leaves the 2 behind. We know that 3 squared is going to be 9, because we're going to cancel out one of the 3's. It's no longer 3 cubed. 3 cubed is 27, so if we cancel out one, we'll get our 9 there. Then if you notice, we'll essentially have our 9 times the 2 4, or times 4, because 2 times 2 is 4, and then we didn't touch the square root, remember? So this essentially becomes 36 times the square root of 2, and that's essentially what we get when we plug in the 18. So this would be 36 times the square root of 2. The next thing we need to do is plug in the 2. Now the 2 is a little easier because it's a little smaller number than the 18 was, but we plug in the 2 this time. Okay. Same scenario here. So this would be 2 over 3. 2 to the 3 over 2, we'll write that as 2 times the square root of 2. We'll simplify, we'll get 4 times the square root of 2 all over 3. So when we sub in the 2, this is what we get. Now, the 1 over 8 was out there. 36 times the square root of 2 minus 4 times the square root of 2 all over 3. That's where we end up. This is just going to give us, I think it's going to give us 13 times the square root of 2 all over 3. And now we're down to our last integral from 0 to 1. And we'll have 13 times the square root of 2 all over 3. And we're integrating with respect to x now. But this is just a constant. So this is 13 times the square root of 2 all over 3 multiplied by x, evaluated from 0 to 1. And clearly we see that the answer is just going to be 13 times the square root of 2 all over 3. And that's your final answer for the surface integral. So your final answer for this surface integral is going to be 13 times the square root of 2 all over 3. So that one was a little involved. So just make sure you have your calculator next to you. That way that you can check your answers. Okay. So I'll post this example on YouTube as well. I believe I have 3 examples up. Well, no, I have 1 example where we actually use the definition of the surface integral to evaluate it like we did in this particular example. And then I think I have 2 other examples where we evaluated the surface integral by parameterization. So this one will be put on YouTube as well. Okay, I will see y'all next time. Reach out if you got questions. Y'all take care.